The binomial theorem. A binomial is an algebraic expression of the sum or the difference of two terms. Let's do an investigation. Expand each of the following and simplify fully. Write your answer on the line. So if you have x plus y to the power of 1, you simply just have x plus y. If you have x plus y squared, you have x plus y times x plus y, which gives us x squared plus xy plus xy plus y squared when we FOIL or expand that. So that gives us x squared, and then these are like variables, so we have 2xy, and at the end here we have plus y squared. X plus y to the power of 3 would be x squared plus 2xy plus y squared. So it would be the previous answer of x plus y squared times another x plus y. If you expand that, see what answer you get. For the same thing here, I want you to take, for x plus y to the power 4, I want you to use your previous answer and then just multiply it by another x plus y. Once you've done these two answers right here, I want you to predict the following without expanding. See if you can figure out what x plus y to the power of 5 would be, or x plus y to the power of 6. All right, what you see before you are some of the answers you should have arrived at. So take a look first at the top half here, and I want you just to look at what x plus y to the power 3 and x plus y to the power 4 looks like. And I have the following for x plus y to the power 5 and 6, and hopefully you came along with that conclusion, but I'll walk you through some of the beauties of it. So let's just look at the x's to start off with. So here we have x plus x to the power 3, then x squared, then a regular x, and then there was no x. On the flip side here, we have y cubed at the end here, y squared over here, y, and then at the end there is no y. So notice that y is increasing from left to right, and x is decreasing from left to right. Same thing happens with x to the power 4, x plus y to the power 4. So we have x to the power 4, then it decreases to x to the 3, 2, x to the power of 1, and then there's no x. And then we have the opposite for y. So on the far right, it's y to the power 4, 3, 2, 1, and then there is no y at the end. Okay? And so notice that the same thing happens in x plus y to the power of 5 and x plus y to the power of 6 in my solution there, and just follow it as we go along. So you see y starting at power 6, then 5, then 4, 3, 2, 1, and then gone. And x to the power of 6 on the left here, then 5, 4, 3, 2, 1, and then gone. Now the final question I haven't addressed yet is, how do these numbers work out? So there's a few ways we can talk about this. So here we have just a 1 and a 1 because there's nothing there. Here we have a 1, then a 2, and then a 1. Here we have a 1, then a 3, 3, and a 1. Well, you'll notice that this is a sum of the previous answer there. So it's 1 plus 2 gives us 3, and 2 plus 1 gives us 3. On the outside we have 1. Here we have a 1, then we have a 4, which is the sum of 1 and 1 and 3. And we have 6, which is the sum of 3 and 3. And we have the 4 here, which is the sum of a 3 and a 1. And then here we end off with a 1. And we have a 1, 5, 10. And you'll notice again, these are the sums. So 1 plus 4 is 5, and 4 plus 6 is 10, and 6 plus 4 is 10, and 4 plus 1 is 5, and then lastly we have our 1 again. Those are really interesting patterns that pop up here. So how does the degree of each term relate to the power of the binomial? Well, if you look at each of these terms, we have here x to the power of 6. Here we have a 5 and a 1 as exponent, 4 and 2, 3 and 3, 2 and 4, 1 and 5, and a 6. And you'll notice that the sum of the exponents is the power of the binomial. So here we have a 6, and each of the terms have a sum of 6 in the exponents. And you'll notice the same thing with our 5 here. Here we have a power of 5, and each one of these terms has a sum of the powers of 5. How do the expansions relate to Pascal's triangle? Well, let's take a look again. Here we had let's look at row 3, or x to the power of plus y to the power of 3. So here we have a 1, a 3, and a 3, and a 1. And if we look at Pascal's triangle, the third row of Pascal's triangle is 1, 3, 3, 1. The fourth row is 1, 4, 6, 4, 1. So where do we see that? Well, that is in the fourth power. So we have 1, 4, 6, 4, and a 1. And the fifth row right here is 1, 5, 10, 10, 5, 1. If you look at the fifth row of Pascal's triangle, in fact, it's 1, 5, 10, 10, 5, 1. So how is it related? Well, the row number is the sorry, I said that wrong. The row values of the nth row are the coefficients for the expansion. Okay? Now, it's a bit more of a complicated way of looking at the coefficients. So let's just back up to make sure we understand. So if I were looking at the 7th row, so if I was doing x plus y to the power of 7, we know that the coefficients would come from the 7th row of Pascal's triangle. And so we know that the numbers are 1, 7, 21, 35, 35, 21, 7, and 1. Okay? So, what if we didn't have Pascal's triangle in front of us and we didn't want to write out the whole thing? Is there another way? Well, as we've seen earlier, Pascal's triangle is also related to combinatorics. So, here's the general form for a binomial using the binomial theorem. So, we have right here, this is the sum. So, we take the sum of r equals 0 all the way up to n. So, that means that you're going to do r equals 0, then you're going to do r equals 1, then r equals 2, and r equals 3, and you're going to add it, each of those values, until we get to n. Okay, this is a term we use more in calculus. We'll try and understand the basic concept in this class, but it's something more geared towards calculus. So, write out an expansion for the binomial theorem using the NCR notation. Okay, so notice here we have n, and then we're going to go all the way from r equals 0 up to n. So we have 3 as our value. So we're going to do r equals 0, then we're going to do r equals 1, then r equals 2, and then r equals 3. Okay, because that's n in this term, and there are 3 is the value then. So r equals 0. So n we have right here is 3, and we know that. So we do 3, choose 0. That's using this part of the binomial theorem. So that's 3, and we're choosing 0 because that right now that is what we're testing. Then we do a. So a is right here to the power of n minus r. So n was 3, and we're minusing 0. And then we put b to the power of r, and in this situation it's 0. Again, we're doing the sum of each of the values. So now we put a plus symbol, and now we're going to test out r equals 1. So now we do again, n is 3, choosing 1. And then we have a to the power of n minus r. n is 3, and in this situation we're doing 1 for r, so 3 minus 1. And then b to the power of r, which is 1. Plus r equals 2. So it's 3, choose, and this time it's 2. A to the power of 3 minus 2, and b to the power of 2. Plus 3, choose 3. And that's a to the power of 3 minus 3, and b to the power of 3. All right. If you were to punch this into your calculator, if you punch in 3, choose 0, you would get a value of 1. Then you would have a to the power of 3 minus 0, which is 3. And b to the power of 0 is just 1, so we can ignore that. Plus 3, choose 1. Type that into your calculator, and you would get 3. A to the power of 3 minus 1, which is 2. And b to the power of 1. Plus 3, choose 2 in your calculator is 3. A to the power of 3 minus 2, which is 1. And b to the power of 2. Plus 3, choose 3, which is 1. A to the power of 3 minus 3, well, that's a to the power of 0, which is just 1. And then b to the power of 3. And you'll notice that this is the same as this line right here, which is x plus y to the power of 3. So we have the same values in there, except for we have a's and b's instead of x's and y's. So the binomial theorem does work for this situation. In this situation, it seems very complicated and unnecessary, but it's a skill that will prove useful when we get into more complicated situations. Okay, let's use Pascal's triangle to write out the expansion of 5x minus 1 to the power of 4. So because of this, we know that we're looking at the 4th row. So I like to write it out this way. So I'm just going to write 1, I'm going to leave a space, plus 4, plus 6, I believe, plus 4, plus 1. And I get out another color. Now I'm going to expand this. So this is my a value, and b is right here. So a is 5x in this situation, and b is negative 1. So notice we don't have the simple stuff we had before, which we just had a and b, or before we had x and y. But now we actually have values that are different than that, larger than that. So we're going to plug in 5x as my first value, and remember that it starts off as going to the power of 4, and then it's 5x to the power of 3, 5x to the power of 2, 5x to the power of 1, and then there is no 5x. On the opposite side here we have negative 1, and so remember negative 1 starts off to the power of 4 on the right side, then to the power of 3, power of 2, power of 1, and then it's gone. Okay, how do you expand this now? So let's actually simplify this expression. So we need to remember some of our exponent rules here. I like to deal with my exponents first, and then as my final step, multiply everything else. Okay, so 5 to the power of 4 is 625, and x to the power of 4 is just x to the power of 4, plus 4 times. Then we do 5 to the power of 3, which is 125, and x to the power of 3, and we have negative 1. Plus 6. 5x squared is 25x squared. And negative 1 squared is a positive 1, because a negative 1 times a negative 1 is positive. Plus 4 times 5x times negative 1 to the power of 3. If you have 3 of them, negative 1 times negative 1 times negative 1, you have a negative number. Plus 1 and negative 1 to the power of 4 is now positive. My final step, I just expand each of the terms. So 1 times 625, x to the power of 4 is 625 x to the 4. Next one. Plus 4 times 125x cubed times negative 1. Well, that's a positive times a negative. So this is actually going to be a negative number. And that gives us 500x cubed. Next. We have 6 times 25 times 1, which gives us 150x squared. Next, we have 4 times 5x times negative 1. That will give us a negative number, and that is 20x. And then lastly, we have 1 times 1, which is plus 1. So notice that our final answer here, though it is correct, it doesn't really show the Pascal's triangle the same way that we saw it before, and that's simply because we have a 5x out in front, and that changes things quite a lot, because all of a sudden the 5 is expanding and it gets quite large very quickly when it has a power. But if you look at the first step here, we can see how it relates to Pascal's triangle very easily, and there's a nice and beautiful pattern here. Okay, let's use the binomial theorem this time, as required before, to expand the expression 3a minus 2b to the power of 3. So again, this is the third row, so n equals 3. So our terms are going to be 3, choose 0. Then it's going to be 3, choose 1. Then 3, choose 2. And then 3, choose 3. Our first value here is 3a, and so it will be 3a to the power of 3, then 3a to the power of 2, 3a to the power of 1, and then there will be no 3a at the end. And then lastly, we have this negative 2b. Make sure you take this symbol with it. So it'll be on the right side, negative 2b to the power of 3, then it will decrease negative 2b to the power of 2, negative 2b to the power of 1, and then no negative 2b. Again, to follow the pattern, I like to deal with each separate section and just expand. So 3 choose 0 is 1, and 3a to the power of 3 is 27a cubed. 3 choose 1 is 3. 3a squared is 9a squared times negative 2b plus 3 choose 2 is 3 times 3a, and negative 2b to the power of 2 is positive 4b squared. And then 3 choose 3 is 1, and negative 2b to the power of 3 is negative 8b cubed. Notice that that one is negative because it's negative 2 times negative 2 times negative 2, and 3 of them makes it negative. Last step that I do is just expand each term. So we have 27a cubed plus 3 times 9 times negative 2 would give me negative 54 a squared b. Then 3 times 3 times 4 gives me 36 a b squared. And lastly, we have 1 times negative 8b squared, which is negative 8b cubed. You will notice a nice little pattern that pops up. Whenever you have this negative symbol right there, or negative symbol right there, the pattern is here we have a positive, then a negative, then a positive, then a negative. And we had it up here too, a positive, negative, positive, negative, positive. It will just go back and forth between positives and negatives. But that only happens when you have a subtract symbol in between the two terms in the original binomial. All right, lastly, just to show off some skills here in our exponent skills, expand and simplify 1 plus 1 over x squared to the power 3. So I like my Pascal triangle method, so I'm just going to steal row 3, which gives me 1, 3, 3, and 1. Take this first term and we'll put 1 to the power of 3. Sorry, I'll change the color of that. Let's be consistent. So that's 1 to the power of 3, 1 to the power of 2, 1 to the power of 1, and then no 1. And then lastly, we have our 1 over x squared term. That's the second term there. So that's 1 over x squared to the power of 3, 1 over x squared to the power of 2, 1 over x squared to the power of 1, and then no 1 over x squared. Okay, let's bring in the exponents here. So we got 1 times, and 1 to the power of 3 is just 1 times 1 times 1, which is 1, plus 3. 1 squared is 1, and we have 1 over x squared, plus 3 times 1. 1 over x squared, just a little review here. If you have a over b and you square it, what you have is a squared over b squared. And that's because a over b squared just means a over b times a over b, which means we're just multiplying the numerators and multiplying the denominators. So 1 over x squared is equal to 1 squared, which is 1, over x squared to the power of 2, and x squared, here's another rule, if you have x to the power of a to the power of b, we actually multiply the exponent, so it's a times b. So that's 2 times 2, which is x to the power of 4, plus 1 over, so 1 to the power of 3 is 1, and x squared to the power of 3 is x to the power of 6, again, because you multiply the exponents. So our final step, we multiply each term, so 1 times 1 is 1, plus 3 times 1 times 1 over x squared. We can think of this as being 3 over 1, so that would be 3 over x squared. Again, think of the next term as 3 over 1, so that would give us 3 over x to the power of 4. And lastly, we'd have a 1 and x to the power of 6 over x to the power of 6. All right, if you're into some kind of fun stuff where you need to extend your learning, I'd love for you to try this question out where we expand and simplify x squared plus 2x plus 1 to the power of 2. And I've only taught you how to expand this with a binomial, so really there's no way to do this trinomial. It's just a try hard. It's trying to be cool. But there is a way to do it. And the way to do this, and the hint, and this is just optional, is to think about the idea of, could I factor it? And if I can factor x squared plus 2x plus 1, then I might end up with a binomial, and then I might be able to expand it. Factoring, you'll see that x plus 1 squared is actually equal to x squared plus 2x plus 1. If you multiply the exponents, we get x plus 1 to the power of 4, and then you can get this final answer right here.